Imagine something so incredibly vast, it warps space and time, yet we're only just beginning to understand how it came to be. What if the very core of every galaxy holds a secret to unimaginable growth, a cosmic engine of immense power? Today, we're diving deep into the heart of darkness to unravel the profound mystery behind supermassive black holes and their insatiable hunger. Right now, you're looking at the center of a galaxy. It's a place of breathtaking beauty and unimaginable chaos. At the very core of this cosmic storm, and nearly every other large galaxy we've observed, including our own Milky Way, lies a supermassive black hole. Now, when we say supermassive, the word barely does it justice. These aren't your typical stellar mass black holes, which are maybe a few dozen times the mass of our sun. No, supermassive black holes, or SMBHs for short, are millions, sometimes billions of times more massive than our sun. They are true cosmic behemoths, gravitational titans that anchor entire galaxies. But this raises a profound question, one that keeps astronomers up at night. How did they get so big? How does something grow to be billions of times the mass of a star? The universe has a few spectacular answers. The first and most common way a supermassive black hole grows is through a process called accretion. Imagine a cosmic drain at the center of the galaxy. Everything that gets too close, stars, gas clouds, dust, is caught in its immense gravitational pull. But it doesn't just fall straight in. Instead, it forms a swirling, flattened whirlpool of superheated matter around the black hole known as an accretion disk. As this material spirals inward, getting closer and closer to the point of no return, the friction and gravitational forces become immense. The matter is squeezed and heated to millions of degrees, causing it to glow brighter than all the stars in the galaxy combined. When a supermassive black hole is actively feeding like this, we call it a quasar. These are some of the most luminous objects in the entire universe, cosmic lighthouses shining from the dawn of time. You might think a black hole could just eat forever, growing infinitely. But there's a cosmic speed limit. The intense light pouring out from the accretion disk actually pushes back on the very material trying to fall in. This outward pressure from radiation counteracts the inward pull of gravity. It's a natural regulator, a cosmic thermostat known as the Eddington limit. This limit puts a cap on how fast a black hole can theoretically grow by just eating gas and dust. So if there's a speed limit, how did they get so mind-bogglingly massive, especially the ones we see in the very early universe? This hints that there must be more to the story, and there is. Galaxies aren't lonely islands in space. They interact, they collide, they merge. And when two galaxies merge, so do their central supermassive black holes. Picture this: two vast galaxies, each with a gravitational monster at its heart, are drawn together over millions of years. Their stars and gas clouds mingle in a chaotic, beautiful dance. Deep within this galactic collision, the two supermassive black holes begin a gravitational waltz of their own. They orbit each other, getting closer and closer, spiraling inward for thousands, even millions of years. In the final moments of their merger, they are moving at a significant fraction of the speed of light. The cataclysmic collision unleashes an immense burst of energy, not as light, but as ripples in the fabric of space-time itself, gravitational waves. Instruments like the future space-based observatory LISA are being designed specifically to detect these powerful cosmic chirps from merging supermassive black holes across the universe. These mergers are a way for black holes to gain mass in huge, discrete chunks, effectively bypassing the slow and steady Eddington limit. Sometimes, the force of this merger can be so asymmetrical that the newly formed larger black hole gets a powerful kick, sending it hurtling through its new host galaxy, or even ejecting it entirely. This recoil effect has profound implications for how galaxies and their central black holes evolve together. But the relationship isn't just one way. A supermassive black hole doesn't just sit there and eat. It profoundly shapes the galaxy it lives in through a process called feedback. As the black hole feeds on its accretion disk, not all the material falls in. Immense magnetic fields can grab some of this superheated matter and launch it away from the black hole at nearly the speed of light. These are the colossal jets you may have seen in astronomical images. Beams of energy that can stretch for hundreds of thousands of light years, far beyond the visible edge of the galaxy itself. These jets, along with powerful winds of radiation blowing off the accretion disk, act like a galactic-scale pressure washer. They blast through the galaxy, heating up and blowing away the cold gas clouds that would otherwise have collapsed to form new stars. In this way, the supermassive black hole acts as a galactic thermostat. When it feeds too quickly, it blasts its surroundings, shutting off its own food supply and quenching star formation. As things quiet down, gas can cool and flow back towards the center, restarting the cycle. This feedback loop is crucial. It explains why large galaxies don't just keep forming stars forever, and it beautifully links the physics of the tiny region around the black hole to the evolution of the entire galaxy, which is trillions of times larger. We can see the signatures of this feedback everywhere, from vast bubbles blown into galactic gas to the observed relationship between a black hole's mass and the properties of its host galaxy. So, we have steady accretion and dramatic mergers. But this still leaves us with one giant mystery: the seeds. How did the very first supermassive black holes get started? We see fully formed billion solar mass black holes in the universe when it was less than 1 billion years old. That's not enough time for a normal stellar mass black hole to grow that large, even with mergers. Scientists are racing to figure this out. One theory suggests that the very first stars, which were hundreds of times more massive than our Sun, could have collapsed directly into intermediate mass black holes, giving them a significant head start. Another, more exotic idea proposes that vast clouds of primordial gas in the early universe could have bypassed forming stars altogether and collapsed directly into a massive black hole seed, weighing tens of thousands of solar masses. Finding these seeds is a primary goal for modern astronomy. Telescopes like the James Webb Space Telescope are peering back to the cosmic dawn, hoping to catch a glimpse of these nascent giants. At the same time, the Event Horizon Telescope, the same collaboration that brought us the first ever image of a black hole, is expanding its network. It aims to create even sharper images and movies of our own galaxy's supermassive black hole, Sagittarius A Chance, and the giant in M87, to test our understanding of accretion and gravity in unprecedented detail. From their mysterious origins as seeds in the dawn of time, to their growth through steady feasts and cataclysmic mergers, to their role as galactic architects, supermassive black holes are not just cosmic curiosities, they are fundamental engines of cosmic evolution. Understanding how they grow is to understand how the universe itself is structured, how galaxies live and die, and how the intricate tapestry of the cosmos was woven. The heart of darkness is not an endpoint, but a beginning, a creative, powerful force that continues to shape the universe we call home. Thank you so much for joining us on this cosmic journey. If you enjoyed this deep dive into the universe's biggest mysteries, make sure to hit that like button and subscribe for more adventures into the cosmos. Let us know in the comments what cosmic question you'd like us to explore next. See you in the next video, and until then, keep looking up.